So in this section, we're going to look at free mechanical vibrations. So remember the differential equation that governs mass spring systems is that the external force, remember in general, F equals ma. If we sum the forces, that equals ma. And in this case, the external force is equal to the inertia times the second derivative of position plus the damping times the first derivative plus the stiffness of the spring times the stretch. This part is essentially Hooke's law, that the farther you stretch a spring, as y gets bigger, the force in the spring is larger. Damping, remember, if that's position, the derivative is velocity. So B times V, that's the force due to air resistance or some resistant force. And then the second derivative of position is acceleration, so this is mass and acceleration. So when we're dealing with free mechanical vibrations, the external force is 0, and we have no damping. So B is 0. So that leaves us with mass times the second derivative, 0 times the first derivative, plus K times Y equals 0. So if we divide both sides by m, we get y squared plus k over m times y equals 0. And we're going to replace k over m with omega squared. So omega is the square root of k over m. In a minute, we'll see why we replace it with omega squared and not just omega. So y squared plus, or I say y squared, be careful here, that's not squared, that's the second derivative, y double prime, plus omega squared y equals 0. So this is homogeneous equation. So our characteristic equation is r squared plus omega squared equals 0. If we subtract omega squared from both sides, r squared is minus omega squared. Take the square root of both sides. Omega squared, that would be a positive value, so we're taking the square root of a negative, so this is imaginary. Square root of omega squared is omega, so omega I. Or we could say 0 plus or minus omega I. So we called k over m omega squared, so that when we move that over and take the square root, we get exactly omega. Solution in the form y equals c1 cosine omega t plus c2 sine omega t. And we can actually express this as y equals a sine omega t plus phi. It turns out when we add those together, we get a sine wave that has an amplitude of a, the period is related to omega, and has this as its phase shift. Now you might say, well, how did you get from here to here? So let's look at a trig identity for when we have sine of angles added together. So if we have two angles added together, we take sine of the first angle times cosine of the second plus cosine of the first sine of the second. Oops. Now cosine of phi is a constant, sine of phi is a constant, because phi is just the phase shift. How much have we've been shifted horizontally, left or right. So if we compare these two, if we distribute A, we get y equals A cosine phi sine omega t plus A sine phi cosine omega t. So that is C2 is A cosine phi, and that's C1, A sine phi. So we want to know what phi and what A is for each of our situations. We already know that how to get omega. Omega is the square root of k over m. But we want to see how, what's A and the amplitude A and the phase shift if we know C1 and C2. So let's solve this one for sine and that one for cosine. So C1 over A is sine. C2 over A is cosine. And remember that sine squared plus cosine squared equals 1. Sine squared plus cosine squared equals 1. So if we square sine, we would square C1 and we would square A. If we square cosine, we would square C2 and square A. And when we add those together, that equals 1. So if we multiply everything by A squared, we would get a C1 squared plus C2 squared equals A squared. Hence, A is the square root of C1 squared plus C2 squared. If we want to solve for phi, notice we can do sine phi over cosine phi. Sine is C1 over A. If we do this divided by that, instead of dividing by that fraction, multiply by its reciprocal. So the A's cancel, so we get C1 over C2. So tangent, and those are supposed to be phis and not thetas. Tangent of phi is C1 over C2. So depending on the signs of C1 and C2, that'll help us know which quadrant phi is in. So once we have A and phi, then we have the solution for our particular equation. So let's put all this together. So the angular frequency is omega, and that's the square root of k over m. The period is 2 pi over omega, 1 over omega. For generic sine or cosine wave, if we call this b, 2 pi over this part here tells us the period. So 2 pi over, in this case, omega is the period. The natural frequency is the reciprocal of the period. So it's omega over 2 pi. The angular frequency is in radians per second. The period is in cycles. The period is in seconds. How long does it take to go through a particular oscillation? And the natural frequency is the number of cycles per second. So from those values, we can we probably have some initial conditions that we'll use to get C1, C2, and then we can find our equation for our situation. Now we want to analyze what happens in terms of how B and M and K affect each other. So one situation is to be underdamped. And that is when B squared is less This is 4mk. Before I continue, let's go back and make a quick comment. In this case that we described where damping was 0 and the external force was 0, this is what is referred to as simple harmonic motion. Notice the function that's driving the motion of it, that y, the height, or if it's a horizontal oscillation, what do I mean by that? We could have either a spring hanging and there's a mass hanging from that and they oscillate up and down, or we could have a mass sitting on like a wheel, a frictionless roller, and then the mass oscillates back and forth. But assuming there's no damping, no friction slowing it down, no air resistance slowing it down this way, then our position is just a simple sine wave. Hence, simple harmonic motion. It oscillates, it's in harmony. But then if we have situations where, okay, we do have some damping in there, then we need to find out, depending on how strong that damping force is, are we under damped, are we over damped, are we critically damped, and what all does that even mean? So let's go back to our generic. We have my double prime plus by prime plus ky equals our external force, which we're doing this as a homogeneous, so no external force for right now. So if this is our, then that would make our auxiliary equation m r squared plus br plus k equals 0. So this is just a simple quadratic equation depending on m, b, and k. So the solutions, the values of r, are given by the opposite of that middle one, plus or minus the square root of the middle minus 4 times the leading one times the constant over 2 times a. So those are our values of r to determine our solution. So notice if b squared is less than 4mk, if this one is a smaller number than that, for example, I'm just making some numbers up, if b squared is smaller than 4mk, then we have a negative value under the radical. So if we have a negative number underneath the radical, then we can rewrite this as negative b over 2a plus or minus that square root over 2a. And if that's negative, then to make that, let's see, then we're going to have an I out front, and we're going to take the square root of the absolute value of that, which if that's negative, the absolute value would be 4mk minus b squared. And I said 2a, a is m, so that should be m, that should be m, and that should be m. So let's just call this alpha plus beta I, where alpha is negative b over 2m. Beta is the square root of 4mk minus b squared over 2m. So since we have an imaginary complex solution, then our solutions are going to be e to the alpha t cosine beta t plus sine beta t. As we did in the previous case, cosine is going to have a C1 with it, sine is going to have a C2 with it, so that inside part we could rewrite as A sine of omega t plus phi. So we could call this A e alpha t sine of omega t plus phi. For again, alpha is negative b over 2m. Now b is a positive value, m is a positive value, so a negative times a positive divided by a positive is negative, so our exponential here comes out to be negative. So our e to a negative power, that gives us exponential decay, so that from left to right we're getting smaller and smaller and smaller, and as t goes to infinity, e to the negative kt approaches 0. We could write that 1 over e to the kt, and as t gets infinitely large, we have e to an infinite power 1 over infinity, that goes to 0. The sine part, that's making it oscillate. So if we put those two ideas together of oscillation and exponential decay, then when we have an over or an underdamped situation, then we have a situation where we experience some peaks and some troughs, but over time the peaks and troughs are getting shorter and shorter and shorter. And if we looked at in class, if we hung a mass from a spring and we pulled it down, this would be our equilibrium position. If we put it down and let it go, it's going to oscillate up and down, but because of air resistance, those peaks are going to get shorter and shorter and shorter, and if we leave the room and come back later, then it's basically going to be still. It's not going to be oscillating anymore. So this is underdamped, or also referred to oscillatory motion. Let's mention a couple of other things as far as terminology. So our y values are going to range. This is going to affect our amplitude. So sine, the largest value for sine is 1 and the smallest is negative 1. So if this is as big as possible, then the largest this could be would be a e to the alpha t. If sine is negative 1, then we could have negative a e to the alpha t. So our amplitude is going to be somewhere in that region, and our amplitudes are going to be changing. Now, since it's oscillating and it's not purely simple harmonic motion, then instead of calling it a period, we call it a quasi-period. And the quasi-period is 2 pi over beta. So whatever our beta is, and I guess I should in this case use beta here instead of omega. So beta, 2 pi over beta, as we define beta up here, that gives us our quasi-period, our quasi-frequency. Frequency is the reciprocal of period, so our quasi-frequency is either b over 2 pi, or we could call that 1 over p. And again, we refer to this as being underdamped. It's damped, meaning that we're affecting our amplitudes and we're shrinking them because it's being affected by a resistant force, but it's not critically damped, or it's not damped to the point that it no longer oscillates. So the next situation we'll look at, so let's write our differential equation again. is going to be where b squared is greater than 4mk. So when we write our characteristic equation or our auxiliary equation, again, the solutions come from the quadratic formula, so opposite of b plus or minus the square root of b squared minus 4 times m times k, all of that over 2m. So if b squared is bigger than 4mk, then underneath the radical will be a positive. And if underneath that is a positive, then we don't have imaginary solutions. We only have real solutions. And if we have real solutions, they're of the form e to the, what letter are they going to use? R1t and R2t. So R1 and R2 are just going to be your real numbered values. Put this down. They come from that quadratic equation. When systems are overdamped, we have a couple of things that could happen. And let's just look at a sketch. So we could have that we start at a highest point that's as far up as it goes, and then it just decays to nothing. In that case, we have no local max or min, so no local extrema. We could have the situation that when we start, it's still on the way up, but because it's so overly damped, it has so much resistance, it doesn't get to go below equilibrium, so it's slowing it down. So we have one local max, or we can have a situation where we have one local minimum, where it starts up here and it goes down, but once it reaches this minimum value, it's so damped that it can't get past equilibrium again. You might think of a spring has a mass in it, and maybe you have some, either that mass is really wide and has a large surface area and a low density, or you might put some kind of dampener on it. And then that might be in some medium, some real viscous fluid, so that when you pull it down, that's not what we're wanting. When you pull it down, the resistant force from that viscosity, the spring is wanting to pull it that way, but this fluid in here is so viscous, it's so thick, that it's resisting that, and it may be that that resistant force is so much stronger than the spring force that it doesn't really let it get back to equilibrium. So we reach this minimum position somehow, but then we're not able to get back to equilibrium. Now, if this was air, we wouldn't expect that to happen. We would expect some mild oscillations regardless of our dampener. But if we were in a thicker fluid than air, then it might not allow us to get back. Think of it like a thick mud or a cement or something. We might pull it down, and that spring might pull us back towards equilibrium, but never quite reach there. So that's an overdamped situation. If we want to find the maximums or minimums, remember how you do that. To get a maximum or a minimum, you have to take the first derivative, set your first derivative equal to 0 to find your critical points, and since we only have at most one peak or one trough, our first critical point is going to be where either our maximum or our minimum occurs. So our rules of maximum and minimums still apply. We just need to find out how we can get that. So the other situation we want to look at is critically damped, and what that's going to look like, how that's going to happen. So critically damped is, if we go back to our equation, and we'll skip right to the part where we get R. we've looked at where we get a negative number under the radical because this was smaller. We looked at where we get a positive number under the radical because this is larger. But the situation we haven't looked at is when b squared and 4mk are equal. If they're equal, then they have a difference of 0. Square root of 0 is 0. Plus or minus 0 is just this. So we have a single repeated solution. So instead of having two different r values, we have a single r value that's basically a repeated one. So that means our solution is going to be c1 e to the rt plus c2t e to the rt, where r is given by negative b over, I keep on writing a, so used to the quadratic formula, that's 2m. So if b squared and 4mk are equal, r is just going to be negative b over 2m, and that will be the format of our solution. Let's look at kind of what's going to happen to this over time as t goes towards infinity. So let's factor the e to the rt out. I'm just going to put it down here on the end. So if we factor that out, we have a c1 plus a c2t. R, we've said what r is, so we can replace r with negative b over 2m. We can make this a fraction. We have a negative exponent, so we can move this to the denominator and call this c1 plus c2t over e to the b over 2mt. And we can look at this and try to figure out what is happening to this over time. Is it oscillating back and forth? Is it going for a particular value? If we let t go to infinity, the numerator goes to infinity, and so does the denominator. If b over 2m is positive, t is infinite, e to the infinity is infinity. So that's indeterminate. So we can use L'Hopital's rule to see what this is going towards. If we take the derivative of the top, the derivative of a constant is 0, so we get c2. The derivative of the bottom is e to the x times the derivative of the exponent, or e to the u times the derivative of the exponent. The derivative of the exponent is b over 2m. So if we take the limit of that, as t goes to infinity, the numerator is a constant. That's a constant, but t is going to infinity. So e to the infinity is infinitely big. Infinity times a constant is infinity, because that's positive. A constant divided by infinity, that goes to 0. So just like the damped situation, the overdamped, the underdamped, all of those are going to 0. So what is this critically damped? What does this mean? This is essentially the point that separates us from oscillating and not oscillating. When we go back and look at the overdamped, we didn't have any oscillation. Our amplitude went to 0, but we didn't ever oscillate. Even in the underdamped, our amplitude eventually goes to 0, but the difference is we have oscillation there. We have, if b squared is less than 4mk, we oscillate. That's underdamped. If b squared is more than 4mk, there is no oscillation, so that's overdamped. So the part that separates it, oscillating and not oscillating, that's where the two sides are equal. So that's critically damped. If b was any smaller, then b squared would be less than 4mk and we'd start to oscillate. So there's no oscillation if b squared is bigger or if it's equal. It's only oscillating if b squared is smaller. So this is the smallest value b can become and not oscillate. So that's why it's called critically damped. It is the critical value for this oscillating.